Whereas in type B you can observe that this mesh is coarse in nature, this is coarse mesh type, here you see. So, one is one case for fine mesh case, the distance is taken at a point of 0.40 and 1 t, and for a coarse mesh case the distance is taken for type A types of hotspot stress calculation 0.5 t and 1.5 t, this 2 point. Now, how this extrapolation is done, everything I will just discuss. And for type for this is generally for linear types extrapolation, linear type extrapolation. So, for linear types of extrapolation generally 2 points are required, but in some cases where the stress is very stiff and where the stress is non-linear in nature, very non-linear in nature near the whale toe zone, that means toward the whale toe zone, if the stress is very non-linear in nature, there instead of 2 point, there we need to take 3 point. So, for that generally you see here I have shown figure 3, here you can see here generally 3 point we have taken, this 3 point where we use and we generally do the quadratic extrapolation, and based on this quadratic extrapolation we can find out what is called type A types of what is called hotspot stress. So, whenever the distance taken from the toe location is a function of t, this method in case of type A types of what is called hotspot stress calculation. But constant distance, like you see this is type B stress calculation, you can see at the last figure, this is the last figure. So, in this figure you can observe the distance is taken which is a constant distance, that is 4 millimeter, 8 millimeter and 12 millimeter. So, after this 3 point stress value we need to calculate, based on this 3 point stress value we need to do the quadratic extrapolation, and we need to find out what is the hotspot stress. You can say the red color way I have written, this is the hotspot stress. Similarly, here in case of type A types of hotspot stress where the distance is a function of t, here also I have written for quadratic hotspot stress, here red color way I have written. For linear purpose also I have used what I am telling, understand, this is also for linear purpose, generally these are the things we use, what I am telling, understand. So, here one thing you should keep it in mind, the extrapolation method can be linear or quadratic, but for both the way if we calculate the hotspot stress according to IIW recommendation, it gives a more conservative types of result. And if hotspot stress method we can use by some other standard also, like based on Eurocode standard, if we calculate the hotspot stress, that case generally whatever the hotspot stress we used to get, that is generally comparatively little bit lesser than the hotspot stress calculated by IIW. So, that is why some other standard, like I have written already, some other standard once we use and once we calculate the hotspot stress, that generally gives us what is called high number of cycle, that means that is not more conservative like IIW standard, this you should keep it in mind. Okay. Then also those method, like what happens IIW, and it is observed that IIW and Eurocode standard, this gives a fatigue life estimation which is very close to each other. That is why this IIW and Eurocode 3 is popularly used for calculation of fatigue life using hotspot stress method. That is why I have written that this hotspot stress method, as it gives a very accurate result for fatigue life assessment, that is why this method is good alternative for fatigue design if there are no fatigue detail classes are available. Okay. Now, how to determine this hotspot stress using linear interpolation, that I am showing. So, for linear interpolation, what is the method generally we use, that I am going to show. Let us consider like one example I am just giving, then it will be very clear to you how this linear extrapolation is done. So, let us consider this is the toe which is at the surface of this point, this is the toe point. So, in this location whatever the stress we need to find out. For finding out this thing, what are the thing required to do? We need to find out according to IIWA standard, let this is the distance at point 40 from the toe, let toe is origin O, okay, 0 distance, and at a point of 1.0 t. Okay. So, generally for hotspot method in type A, here mesh size, here one thing you should keep it in your mind, in mesh size not more than 0.4 t around the well toe zone, this you should keep it in mind. And how this linear extrapolation is done? So, what happens at 0.4 t, let us consider a stress value is this, and for 0.1 t let us consider the stress value is this. So, at 0.1 t let us consider this stress value is sigma 1 t, and at 0.4 t let us consider the stress value is sigma 0.4 t. Okay. So, by this we need to generally draw a straight line. Let us consider this 2 point, we need to draw a straight line. This straight line we need to extrapolate up to which position? Up to the toe position. Toe position means this is the toe line you can say. So, this at this toe position whatever the stress we will get, this is generally called hot spot stress, sigma s. This sigma s how we can calculate, that I am just going to show by using what is called extrapolation techniques. So, this extrapolation technique you can write like this, ratio of this first what is called sigma, let us consider 0.4 t minus let us sigma hotspot stress. So, sigma 40 have a distance, let us consider this has a distance is 0.4 t, okay, minus, and sigma s distance is at 0. So, this should be equal to, we can write as sigma 1 t minus sigma 0.4 t divided by, what are the things we should write? Let us consider this is from here to here, this is 1 point t. So, you can write 1.0 t minus 0.4 t. So, by using this relationship we can easily find out what is called hotspot stress using IIWA standard at a point of 0.4 t and 1 t stress distribution. So, that if you just do the calculation, the stress distribution is represented will be 1.67 sigma 0.4 t stress minus 0.67 into 1.0 t, what I am telling, understand. So, it is very simple calculation you can say. So, you see hotspot stress at 0.4 t minus sigma, that means stress at 0.4 t minus sigma s. So, what is the distance of 0.4 t? That distance minus distance of sigma s, which is considered a origin, that is why 0 distance. Similarly, at 1 t, this 1 t and 0.4 t, this 2 minus should be equal to this 2 stress and subtraction should be equal divided by 1 t minus 4 t. So, if we do the calculation, we can easily find out what is called the stress value. Okay. So, linear extrapolation we can represent in a very what is called a simple equation, like let us consider this is. So, one simple equation I am writing, then this equation also you can use. So, this is 0, this is 1 point, generalized equation. So, this is 1 point, this is 2 point, okay. So, from here to here let us consider the distance is d1, and another point let us consider from here to here this distance is from this origin is d2. Okay. Now, so here generally let us consider the stress is sigma 2 and this is sigma 1. Okay. This is 1 point, 2 point. Okay. So, after that we need to just add this 1 2 point and extrapolate this sigma s we will get. So, by this generally directly we can find write the equation. What should be the sigma hs? Sigma hs you can write as directly I am writing sigma 1 plus d1 by d2 minus d1, okay, into sigma 1 minus sigma 2 into sigma 1 minus sigma 2. Very simple, whatever the things left side I have shown, these things only here right side in general form we are taking. So, this is the linear extrapolation. Here the mesh size is less than, you can say not more than 0.40 you can say. That is why what happens, this is called fine mesh case. So, in case of fine mesh case we can use 3 point for what is called quadratic types of extrapolation. So, for quadratic types of extrapolation this 3 point we need to consider as little bit here also I am just showing. This point is 0.40 according to IIW standard, another one is 0.90, in previous slide itself I have shown 0.40, 0.90 here you can see in this figure you can see. So, 0.40, 0.90 and 1.40. These 3 point stress value we need to consider. So, here I have written. So, here how to do the extrapolation, that we need to know. So, here generally the extrapolation method is a very interesting method. So, here we need to consider a quadratic equation. Let us the quadratic equation in terms of a function, let us consider sigma x, where x is a function of t equal to sigma t. You can write as this equal to, you can write as a t square plus b t plus c. What I am telling, understand. So, based on this 3 point stress value, 3 point stress value means one stress will be sigma 0.40, another stress will be sigma 0.90 and another stress will be sigma 1.40. So, based on this you can say 3 known data which we can find out from FEM result, and this is for fine mesh case actually, you should keep it in mind. If it is coarse mesh case, then there will be some other approach, that also I will show. So, by using this and by using this quadratic equation, let us consider this quadratic equation 1. So, we can find out A, B or C. So, this A, B, C actually is a coefficient, this A, B, C which generally are the coefficient of this quadratic equation 1. So, this A, B, C we can easily find out based on this equation number 1. So, from this equation number 1, whatever the C value we will get, this C value will give us the hot spot stress. This you should keep it in mind. So, this C value generally we have calculated for this according to IIW standard, considering the mesh size less than equal to 0.40. Okay. And the point of this stress we have taken at a distance of, you can say at a distance from the weld, this is the weld toe, from this weld toe this is the origin point, you can say this is the origin. So, at a distance 0.40, whatever the stress value 0.90, this 2 and another is we have taken as 1.40. So, in this 3 location we find out the stress value, after that a quadratic curve once we fit, and that quadratic curve we need to extrapolate. You see, let us consider the stress value is like this. After extrapolation, whatever the stress value we will get sigma s, this sigma s is represented as a function of stress at this 3 point. What I am telling, understand? This is represented in equation number 2. This you should keep it in mind. Now, another case also I have shown, Then generally we can use coarse mesh also. This coarse mesh once we will use, there generally we need to consider higher order element. Higher order element means that element generally should have more number of node, you can say. So, there the shape function should be should not be a linear types of thing. This should be a polynomial or higher order types of shape function we need to use there. So, I am not going in details more details about those FEM types of concept. So, just you should keep it in mind, for coarse types of mesh we need to consider higher order element. Higher order element means it not only have a point of the element at corner, there should be some location or node point in between that, what it is called, you can say corner point of that element. What I am telling, understand? Let us consider this is a 2 dimensional what is called element. So, here generally this is this corner point generally called node you see, and apart from this corner point, if some other nodes are there at in between this corner point, then those types of element is called higher order element. So, that is why what happens for coarse types of mesh, higher order element, and here generally length of the element is considered as equal to the plate thickness at the hot spot zone. This you should keep it in mind. So, here the whatever the length of the element, here you can see in this figure B we have shown this coarse mesh. So, here the mesh element size here you see is considered as equal to the thickness of the plate. So, due to this higher order, you can predict the stress value in between this element also, this middle point, here you see this is one middle point, this is another middle point. Okay. We can evaluate the stress at well toe by considering the stress value for coarse mesh case. The stress value we need to consider there at a point T and at a point 1.5 T. These two location we should consider there. So, in this two location, whatever the stress value will be there, that will be sigma 0.5 T and this will be sigma 1.5 T. Okay. This two stress value we will get. So, based on this two stress value, here you see this two stress value we need to find out in between the element edge. You see element edge, let us consider this is one point, this is another point. You can see this is generally whenever we consider this is coarse mesh for type A type of hot spot stress calculation purpose, generally these types of coarse mesh we need to use. And here always you should keep it in mind, here generally always the distance of the stress value should be a function of T for type A types of stress distribution. That is why based on this 0.5 T and 1.5 T stress value, if we do the extrapolation, you see if we do it the extrapolation up to hot spot edge, you can see up to hot spot stress, then we can easily find out by extrapolation method, whatever the extrapolation method I have shown, like this equation. Let us by using this equation right side, you can see by using this equation we can easily find out hot spot stress which is shown here. Okay. This you can see. This is called linear extrapolation method for coarse mesh types of structure, and for fine mesh types of structure, linear and as well as what is called quadratic types of extrapolation I have shown in equation number 1 and 2. These are generally used once the toe is lying on the surface of the plate. This you should keep it in mind, and which is generally for type A types of hot spot point, and this is also called type A types of hot spot stress. This you should keep it in mind. Now, we will discuss about type B types of hot spot stress. For type B, generally instead of taking the stress location at a as a function of T, there we need to consider the stress location is a absolute distance from the toe location. Like here you see for type B, I have already told you, generally here we need to take the, this is the toe in figure, here I am just showing in figure for fine mesh case, this is the toe. From toe we need to take, you see a distance, first distance point is 4 mm, second distance point is 8 mm and third distance point you see second and this is third. So, third distance point is 12 mm. So, these 3 points generally we use for what? For quadratic types of extrapolation. This is we use for quadratic type of extrapolation. And for coarse mesh case, this is coarse mesh case. In finite element method, generally this meshing is required to do what I am telling, and that is why it is called for coarse mesh means for a element whose length is equal to the thickness of the plate. For that case, generally what happens? Let us consider plate thickness is 10 mm. So, for that case, generally we need to consider 2 points which have a distance 5 mm and 15 mm away from this what is called toe point. This is the toe point. Okay. So, at 0.5 mm whatever the stress value will be there, that stress sigma 0.5 T we will get, and whatever the stress value at 1.5 T will get, that is 1.5 T, that stress value will get. This 2 stress value we need to draw a straight line. After that, this we need to extrapolate up to well toe location. At that location whatever the stress value will be there, that is called hot spot stress using coarse mesh approach. So, this I have shown in equation number 5. This is generally used for what is called hot spot approach calculation for type B types of hot spot point. So, here one thing you should keep it in mind, for fine mesh case generally this mesh edge length, that means element edge length should not be more than 4 millimeter. This you should keep it in mind. And for coarse mesh case generally, which I have already told you, it generally should be what is called within a range of thickness of the plate. This you should keep it in mind. So, how to extrapolate the hot spot stress using finite element method, that I have already discussed both for type A and type B. So, you got the idea how to predict the hot spot stress value. Now, this hot spot stress also we can estimate by experimental observation also. In experimental observation purpose, generally directly we cannot predict the stress value. Okay. Generally there for predicting the stress value, what we used to do, first of all we need to find out the strain value on that particular location. That location for IIW approach I have already told, that means here I have shown, just here you see, according to IIW standard from well toe zone at a distance of 0.4 T, we need to put a strain gauge, what I am telling, understand. So, first strain gauge here we need to put using type A types of, you see type A types of hot spot stress calculation. In figure you can see this is on strain gauge, this is called strain gauge, strain gauge. This strain gauge generally we use to find out what is the strain value due to the structure subjected to loading, what should be the strain value here. So, this strain value we can represent it as 0.4 T. Similarly, at a location 1 T we need to put another strain gauge, there generally the strain value will be 1 T. Okay. These two strain gauge we need to insert there, and we need to apply the load on this structure. Based on this load amplitude, whatever the strain value we will get at 0.4 T and 1 T location, that based on this strain value we can find out what should be the strain value, what is called what should be the strain value in well toe. That well toe strain value is called hot spot strain. So, that hot spot strain generally we need to calculate here, you can see by using equation number 6. So, same extrapolation, linear extrapolation we have done. Now, this is one way we can find out the hot spot strain value, and another case for quadratic types of strain value I have already told you, if the strain distribution is non-linear in nature and stiff, and if it is varying toward the well to very non-linear way, there in that case generally what happens, this non-linear strain measurement is required to do. That is why 3 location we have used to choose, that is 0.40, 0.90 and 1.40. So, in this 3 location we need to put this strain gauge. Now, this strain gauge once it is subjected to some loading, it will either expand or contract, whatever it is, generally it will, if it is tensile types of load, it will expand. So, due to this expansion of this strain gauge, generally we can find out what is the strain value in that location. That strain value once we calculate strain gauge, you know how it's look like, you know it is a electronics device, you can say it's look like just this. Okay. This strain gauge generally we need to insert, after polishing that location we need to insert in that particular location, like in this location we need to insert this strain gauge. This strain gauge generally connected with a data logger system. This is connected to a what is called data logging device, that is DAQ. Let us consider DAQ. This DAQ generally connected to a, you can say, computer monitor, you can say computer. So, by this from this computer generally, and DAQ means data acquisition system. With this system generally we can predict once the structure is subjected to loading, how much expansion or contraction in this strain gauge. Strain gauge means a very thin types of you can say film types, what it is called filament types of what is called wire, very thin filament types of wire is there. Once it is subjected to expansion and contraction, here generally it is calibrate this expansion and contraction by this DAQ system. From DAQ system with the help of computer we can extract the strain value. What I am telling, understand? Now, once we calculate this strain value by using quadratic or what is called linear extrapolation, this strain value once we multiply with Young modulus, if the strain value generally, if we consider generally the strain value within elastic limit, then directly we can use the linear relationship there, and there generally we can use what is called Hooke's law. This Hooke's law, what is Hooke's law? Sigma is equal to E into epsilon. So, for elastic range generally the hotspot state generally consider, if we consider within a elastic range, then this hotspot state will be whatever the Young modulus will be there, E into epsilon, whatever the hotspot strain we calculate. By using this relationship we can easily find out what is the hotspot stress experimentally, what I am telling, understand. So, this is generally type A. Similarly, for type B type of purpose also same procedure we need to use. Here also we need to place the strain gauge at a distance of 4 mm, 8 mm and 12 mm. So, at this 4 mm, 8 mm and 12 mm we need to predict the what it is called strain value. This strain value epsilon 4, epsilon 8 and epsilon 12. After that generally we need to do the quadratic extrapolation, which I have already told you, this quadratic extrapolation to the well toe. Then we can easily find out what is the epsilon SS. This is quadratic extrapolation. Similarly, for linear extrapolation also we can do for this purpose, and we can easily find out what is the hotspot strain value. Based on this hotspot strain value, generally with the help of Hooke's law we can predict the hotspot stress value. So, once we calculate this hotspot stress value, you see, that is why here I have written determination of stress based on strain. If the stress state is close to uniaxial types of stress, the approximation to the structural hotspot stress is obtained approximately from the equation 9, which I have shown. So, what is the condition? If the stress state is close to uniaxial type, for that case generally hotspot stress can be approximated by Hooke's law, since stress can be seen as a uniaxial way. Then by this we can predict the hot spot stress. Now, we already find out hot spot stress. Then next what we need to do, this third step, that is we need to find out the number of cycle. For finding out the number of cycle, generally what are the things required to do? This standard relationship is there. This NT is generally considered as 2 into 10 to the power 6 cycle, okay, and phi q is known as failure probability factor. This phi q is known as failure probability factor. This failure probability factor, for different failure probability factor, you see this probability factor value is given in table 1. You can observe that, like 50% probability, the failure probability, the phi q value is 1.3, 2.3 probability, you can say this value is 1, like this. Actually, if the failure probability gradually you can say decrease, then what happens, your phi value also gradually decrease. You can observe from this what is called table 1. With the help of this, generally we can calculate what is the number of cycle. So, now here whatever the FAD value used in this equation number 10, that also I will now show in subsequent slide. And what is the M value? Generally M value is the slope of this SN curve, which will be used for determining this life. Accordingly, generally we need to consider this M value. Generally this M value is equal to 3 we use, okay. And this FAD value, what are the FAD class are there, that I am going to show. So, generally for hot spot purpose, here also the shape of the fatigue strain, that means SN curve, in IIW recommendation for a structural hot spot stress are similar to what is called direct nominal stress curve. You can see in direct nominal stress curve also SN curve we use. Whatever the SN curve there, it is also similar according to IIW standard. And this curve generally consists a line with a slope. You see this curve generally consists a line, here you can see, which is plotted in a log stress range versus you can say number of cycle. So, this log stress range by its number of cycle, here the slope of this curve is 3 up to what, up to a number of cycle of, you can say what it is called 5 million cycle. So, after that generally there we got a what is called cutoff point. After that generally we consider the constant amplitude fatigue limit for a steel types of material. So, that things here only it is showing. So, this fatigue strength SN curve, it consists a line of constant slope 3 in a log plot, and a cutoff limit for a CAFL means constant amplitude fatigue load CAFL at the cutoff limit is at a 5 million cycle. A symmetric what is called SN curve is showing here. Here generally whatever the stress value we got at a number of cycle of 2 into 10 to the power 6, that stress value is called FAT class value or FAT strength value. This is called FAT value. What I am saying, when that earlier equation 10, whatever the things we have shown at that location, whatever the stress value at a 2 into 10 to the power 6 cycle we got, that is generally called FAT stress, FAT value. What I am telling, understand? This you should keep it in mind. So, here one thing you should keep it in mind. Marquis and Cahonen in 1996 observed that whatever the pre-standard Eurocode SN curves are there, which are significantly on the safe side. That means Marquis and Cahonen also observed that that Eurocode SN curve also is significantly in safe side. That is why the last revision of Eurocode 3 also has been recommended the same fatigue resistant SN curve as the IIW recommendation. What I am telling, understand? That means IIW recommendation, whatever the curve he recommend, Eurocode 3 also recommend more or less same types of SN curve. Okay. And here Eurocode 3 generally little bit generally I have already shown you IIW curve give us highest, you can say hotspot stress. Euro curve 3 generally give us a hotspot stress which is little bit lower than the IIW standard. That is why this Eurocode 3 provide us a fatigue life which is slightly higher than the IIW standard. That is why I have written it, which gives slightly higher fatigue life for the component, slightly higher. That is why this Eurocode 3 and IIW both the standard we can use for fat calculation. Nowadays, according to the what is called, according to the Eurocode 3 and IIW recommendation, generally 7 types of welds are introduced and one SN curve is recommended for each type. This you should keep it in mind. What are those 7 standard? These 7 standard here you can see in this table 1 and table 2 it is showing. So, here you see, though here 7 different geometry I am showing, but the 7 type geometry have a fat value within a range of only 3 different fat value are there. One is 112, another one is 100 and another one is 90. What I am telling, understand. So, for different types of weld geometry, when we should consider what is called fat value as 112, that is showing. You see this if both side of butt welding is there, first figure you can see, if it is subjected to both axial as well as bending types of loading, then here generally this fat value we need to consider, and both side of welding butt welding is done, then here generally if the welding also fully penetration, there we need to consider the fat value as 112 for hotspot stress calculation purpose. But here you see normal types of both side of weld you can see, and here if this what is called here you can say this first case it is a special quality is very high standard. If it is normal quality and it both side welding is there, for that case you can consider the fat value of 100. What I am telling, and similarly for cruciform types of joint, the fat value is considered as 100 both for axial case as well as bending case. What I am telling, understand. Similarly, here you can say non-load carrying fillet weld, here a fillet welding is done, but the load is applying in this you can say flange, in this flange wave is this is called non-carrying types of fillet weld. For both the case of axial, this is axial types of loading you can say, and this curved line represent bending types of loading. Both axial and bending types of loading, here you can consider a fat value of 100. Similar types of things generally given, and its joint geometry is given for other cases also, like a bracket end of longitudinal stiffener, here also we consider 100. So, these are the different example of fat class and joint geometry detail for hot spot application. Okay. So, these are the references or literatures which I have followed for this lecture. Thank you.